We live on a sphere of rock that spans nearly 13,000 kilometers across. Finding out the exact mass of this planet poses a unique physical problem. There is no scale large enough to weigh it. In the late 17th century, Isaac Newton realized that the invisible force pulling a dropped apple to the ground is the same force keeping the moon tethered in its orbit around the Earth. He eventually mapped that force mathematically. Newton wrote an equation for universal gravitation that could accurately trace the orbits of planets across the solar system. While the mathematics accurately predicted how gravity behaved, they relied on an unknown value, the exact strength of gravitational attraction between known masses, which was required to determine the average density of the Earth. Without knowing how much matter was actually packed into our planet, the true mass of the Earth and every other celestial body in the sky remained a mathematical mystery. Because gravity between everyday objects is weak, early scientists assumed the only way to detect it was by using a massive, naturally occurring terrestrial object. In 1774, a team of astronomers traveled to Schiehallion, an isolated peak in the Scottish Highlands. They chose this mountain because its symmetrical bulk seemed ideal for a massive gravitational test. This diagram illustrates their method. They hung a plumb bob next to the mountain, testing to see if the immense mass of the rock would pull the hanging weight slightly off its vertical axis. The pendulum did deflect. However, a mountain is a jagged, irregular object, and its underground rock density varies. Trying to calculate an exact mathematical value from such a chaotic mass proved inaccurate. The natural universe was too noisy for this level of precision. To weigh the cosmos, scientists realized they needed absolute artificial control. The blueprint for that control came from physicist John Michell, who designed a delicate instrument called a torsion balance. After Michel's death, the project passed to Henry Cavendish, an English scientist known for extreme experimental patience. Cavendish faced a significant challenge. The gravitational pull between two small laboratory-sized objects is less than 1/10,000,000th of the weight of an apple. This animation shows the difficulty. At this scale, even the slightest environmental interference, a faint air current, a vibration from a footstep, or the convection currents generated by a human's body heat, would obscure the results. Cavendish's solution was to systematically exclude the outside world. He rebuilt the apparatus, sealed it inside a 2-foot-thick wooden box, and locked that entire structure inside a closed shed. During the measurements, he never entered the room. Solving the mystery of Earth's mass required Cavendish to isolate his experiment from any external disturbance. Inside the shed hung a 6-foot rod suspended by a thin wire, with small lead spheres at each end. Cavendish placed two 348-pound spheres nearby. Their massive gravitational pull attracted the smaller spheres, causing the rod to rotate and twist the wire. To prevent his own body heat from creating air currents, Cavendish stayed outside. He operated the pulleys to move the heavy weights and read the minuscule fractional movements of the rod through telescopes mounted in the shed walls. The rod oscillated back and forth like a horizontal pendulum. Because the wire had an elastic memory, Cavendish recorded the extremes of these swings and calculated their midpoint to find the true equilibrium position. By tracking a mechanical twist of barely 1/1600ths of an inch, Cavendish captured the uncorrupted force of gravity between two objects on Earth. Knowing the exact amount of twist in the wire, the mass of his lead spheres, and the distance between them, Cavendish could finally calculate the strength of the gravitational attraction. This diagram reflects his final calculation. He determined that the Earth is roughly 5.48 times denser than water. Despite the technology of 1798, his result is within 1% of the modern accepted value. That single ratio provided the final variable. Combining the Earth's size with its newly discovered density allowed scientists to calculate the total mass of the planet, nearly 6 septillion kilograms. Establishing the mass of the Earth created a cosmic domino effect. Because Newton's law of gravity is universal, this terrestrial measurement provided the baseline data needed to determine the true masses of the Moon, the Sun, and the rest of the solar system. Cavendish weighed the world using 2 lead balls in a quiet shed. From his experiments to modern space exploration, understanding the grandest forces of the cosmos has always required mastering the smallest details.